We will now continue with Friederike, who did her master's at the University of Waterloo and now is a PhD student at the Okinawa Institute of Science and Technology in Japan, and has quite some track record in machine learning. So she worked on phase classification and on vortex detection in Bose-Einstein condensates. But today she will talk about self-correcting quantum many-body control using reinforcement learning. Please go ahead. I'm very interested to hear about this topic.
Yeah, so we are trying to tackle the problem of quantum many-body control, which is pretty much essential for most modern quantum technologies. So if you, for example, take quantum simulation and let's say you want to simulate some condensed matter system or some molecule, then you first have to prepare the corresponding ground state on your simulating device. So we are trying to do state preparation. And the idea is that on your quantum device, you start from some initial state that you can easily prepare, for example, some spin polarized state. Where's my mouse? Actually, can I have a laser pointer after all?
Should be here. This is a laser pointer.
Yeah.
Okay.
Is the mouse gone again?
It's gone.
Okay, sorry.
So yeah, we start from some initial state that we can easily prepare. For example, some spin polarized state, and we want to end up in a certain target state. And then the problem is to find a sequence of operators or a sequence of unitaries or gates, which evolves us from our initial state into our desired target state. And then you can get this protocol from your favorite optimal control algorithm. The thing is that these quantum technologies nowadays, they are really based on harnessing many interacting spins or particles. So you really need quantum many-body control. And when you are in this many-body domain, you always have this one big problem that we've also heard a couple of times today, namely that your Hilbert space dimension grows exponentially with your system size. And this makes it infeasible to classically simulate large many-body systems on a classical computer. And so we are trying to address this problem by introducing this new control framework, which first of all is based on reinforcement learning as an algorithm for control. And then we enhance it with matrix product states. And we use matrix product states in two different ways. So one is to actually just compress the quantum many-body state so that we can also efficiently simulate it on a classical computer. But then we also use a matrix product state as a trainable machine learning ansatz for the reinforcement learning agent so that we can also efficiently train. And then our combined framework now looks something like this. So we will always represent our quantum states as matrix product states. And these protocols are devised by some machine learning framework, which by itself is also represented as a matrix product state. And we already had one talk this morning about reinforcement learning, so I won't introduce the details again. The important thing here is that, the algorithm that we use, which is so-called Q-learning. And in Q-learning, we are trying to learn so-called optimal Q values, which are defined as the maximum expected, cumulative reward if you start in a state S and you take action A. So these Q values basically encode the reward structure, and they tell you how promising it is to take a certain action A in a given state S. And then what people do is that they usually approximate these Q values by some parameterized function, and then they try to learn this function. And nowadays, of course, these parameterized functions are usually given by a neural network, which in this case would take as an input the state of the environment and then output one Q value for each different action you can possibly take. And from these Q values, once you've properly learned them, you can then deduce what the optimal action is to take in a given state. And now I want to tell you how we use Q-learning for this quantum many-body control problem. And I first want to tell you of how our environment actually looks like. So what is kind of our setup. And of course, there are different choices you can make, but we considered a spin chain in 1D. And as a reinforcement learning state, we simply choose the quantum state itself that represents the spin chain at a given point in time. And because we are now dealing with a many-body system, we will always represent it as a matrix product state. And then in terms of actions, we will have a set of unitary operators with which we can evolve our quantum state. So this set of unitaries, this is basically our action set. So these are the different actions that our agent can choose. And we will have single particle rotations and these spin-spin interactions. And then finally, the last thing that we have to define is the reward function. And again, to remind you, we are interested in preparing target states. So one quantity you naturally want to maximize is the fidelity, so the overlap between your current quantum state and the target state. The thing is that these overlaps vanish exponentially in your system size, so we actually take the logarithm. So we try to maximize the log fidelity. Okay, and now we come to our agent. So again, to remind you, we are using Q-learning. So our agent is represented by a Q-value network, this Q function here, which takes as an input the quantum state. And our quantum state is now already represented as a matrix product state. So it's actually very natural now to also have a matrix product states as a ansatz, as trainable parameters. And these squares here, you can't really see this right? Oh yeah, here, okay. So the squares here, this is a second matrix product state that has nothing to do with our actual quantum state. And these are literally just parameters that we represented as a matrix product state. And the second matrix product state has this one tensor in the middle with like this dangling leg, which means that the output of the contraction of these two matrix product states is essentially a vector of a certain dimension. And then we feed this vector through a small feed-forward neural network. And the output of this we then interpret as our Q values. And the nice thing about using these matrix product states is that now our resources only scale linear in our system size, opposed to this exponential scaling that we had before. This is, of course, only true as long as our bond dimensions here also don't scale with the system size. Okay, and now we want to see how this actually works in action. So we want to apply it to some state preparation scenario, and we will consider ground state preparation. And so as an example, we just take the mixed field Ising model, which has this phase diagram, just to remind you. So this is for positive coupling strengths and for negative coupling strengths. And now we will choose a specific state and try to prepare it. And in this case, we choose a state on the critical line of the mixed field Ising model. And we try to prepare the state starting from initial states, from initial ground states of the same model, but with opposite coupling strengths. So we are trying to connect ground states of two different Hamiltonians, which is often the case, for example, on quantum simulator platforms. And in this case, we restricted ourselves to 16 spins. So we are trying to control a spin chain with 16 spins now. And now I will show you results of a QMPS agent that we have already successfully trained. So training is over, and now we test it on different initial states. And in this plot, each of these points here corresponds to a different initial state we start from, so with different longitudinal and transverse field values. And the color here corresponds to the final fidelity that we are able to reach with our optimal QMPS protocol, so the final fidelity between our final state and this critical target state. And during training, we set a fidelity threshold that we are trying to reach. And once we reach it, we say we have successfully prepared our target state. So whenever you see like a bluish color in this plot, it means that our QMPS agent actually surpassed the fidelity threshold and successfully prepared our target state. And in these other cases where you see like an orangey color, it means that our QMPS agent failed in preparing the target state. But overall, you see that it actually works really, really well. And there you can already see like a really nice feature of this QMPS framework, namely that our agent can actually devise protocols from various initial states. So we only trained our agent once, but it can now give us all of these optimal protocols for all of these different initial states for free. Then there's another nice thing. So when we were training our QMPS agent, we were only training it from initial ground state that were sampled from this small region there within these white enclosed squares. But now that we test it, we actually see that it's also able to give us optimal protocols well beyond the training region. So our QMPS agent can actually also extrapolate these optimal protocols. And now that this worked so well, we actually also wanted to see how robust our QMPS agent is to noise being present in the time evolution, which is, of course, very important for current quantum technologies, and especially these NISQ devices. And so we looked at different types of noise here. We just present this one. So again, to remind you, when we were training our QMPS agent, we were always evolving with this unitary here on the right, and this time step duration delta t that you see in there. This was something that we fixed, so we didn't optimize over it, and we kept it constant. And now we will randomize it. We will add some Gaussian random noise to it. And here I'm showing you now results where we started from one specific initial state for transverse and longitudinal field values here. And I'm showing you now how the fidelity changes as a function of the protocol step. So it's a time step in the protocol. And please first only look at the red curve. So this is these are the fidelities you would get in the noise-free case, so where we don't add any noise, the deterministic case. And you see that we start off from some small initial fidelity, and then the QMPS agent tries to maximize the fidelity, and then eventually hits the fidelity threshold of 0.97. And now we repeat this again, but now we add the noise, and we do this 5 times with 5 different random seeds. And then this gives rise to these 5 bluish curves that you see. You see that in the beginning, the fidelities still kind of overlap, but then eventually they start to deviate due to the noise. And then again, eventually, the QMPS agent actually starts adapting to the noise. So it starts taking different actions. It really starts adapting the protocol to make up for the mistakes caused by the noise. But in each of these cases, you see that eventually we still hit the fidelity threshold and are successful in preparing our target state. And this was, of course, just one initial state, so we can also now repeat this for all these different initial states, and you see that it still works really, really well, and our agent is actually quite robust to that type of noise. And this is, again, another really nice feature, namely that our QMPS agent can really self-correct the protocols while it's being time-evolved, like on the fly. And we've also considered more examples. So we, for example, also show that if you train on a small system of just 4 spins, you can also do something like universal state preparation. So you can prepare a target state starting from literally any initial arbitrary quantum state. And you can also do like truly many-body state preparation. So really work in a regime that is beyond exact techniques. And then there are also many different directions we can take it from here. And if you have any questions, feel free to ask me, or also Marine, who is also here. And yeah, that's it. Thank you.
Thank you very much for the nice talk. Do we have any questions from the audience? Let me get the second microphone. Thanks. Okay, then maybe in the meantime, I can ask one myself. Probably the classic question you've heard many times. Do you see an immediate extension to 2D? So far you looked at a 1D system, right? It's an MPS description that you use. Do you see any way how one can somehow generalize that?
Well, first, like you could of course map your 2D system to like an MPS when you have problems with like entanglement. You can also try like some higher dimensional tensor networks like PEPs, but then you have other issues, of course. So you can't. You have to resort to approximations and so on. So in this case, of course, it's only for 1D, but you can of course think about extensions here.
Okay. Thanks. Yeah.
Hi there. If you could go back a slide. The fidelity plots, the first one, it appears to have some clear linearity structure originating from the origin. Is that a product of the system, the model, or the training?
You mean?
I don't know. To me, it looks like there's rays coming almost from the origin.
Like, I don't think it has necessarily anything to do with like the training or the ansatz. So the thing is, of course, that if quantum states are like similar, you would end up thinking that the protocols look similar. And I think that this is maybe what happens here, that the states along these lines are somewhat similar because they all kind of point into like the same direction, and therefore you would apply, or you would get the same fidelities in the end.
Right. So the stronger techniques kind of highlight themselves. Is that what you're saying?
The stronger technique?
As in the better techniques seem to be highlighted along certain rays. Is that?
I wouldn't necessarily. What do you define as like better techniques?
Initialization sequences. I don't know how you would describe it.
Yeah, I don't know if you can really say if one is better or not. So here in this case, it's just like a proof of principle that you can get to the target state from all of these different initial states. So it's not that we favor like one initial state from the other. But of course, if you can prepare all of these initial states on your quantum device easily, then for example, you could figure out, okay, what is now from which initial state do I get the shortest protocol that gets me to my target state? Yeah, maybe you can do something like this. Yeah.
Okay, thank you very much.
Any more questions?
So thank you for the presentation. I had a general question about the methodology here. So you're simulating a quantum system with a classical computer, right? So that's the whole point of using this matrix product state, and that's a great job. And you use also reinforcement learning to prepare the state. So how this work would actually map to a real quantum computer? So how this work could help preparing state on a real quantum computer?
Yeah. So first of all, no one stops you, of course, using simulated data to train this and get the protocols and then take the protocols and actually apply them in an experiment. Otherwise, if you want to use experimental data, then currently what you would have to do is actually full quantum state tomography, because this agent takes as an input the full quantum state. Well, we all know quantum state tomography can be exponentially expensive. But in principle, this is something you could do. Another thing you can also do, if you also want kind of part of the training or part of the architecture to already be on your quantum device, is that you can actually map matrix product states to quantum circuits, and then at least part of this architecture can be performed already on the quantum device automatically. Yeah, and you can also do this efficiently, this mapping. Yeah.
Okay, thank you very much.
Thank you for the talk. So my question is more on the reinforcement learning side. I'm not a quantum physicist or anything. So I wanted to ask about the reward function that you modeled. So do you give a reward for every state that you reach? Or do you give like the reward at the end? Or
No, we give the reward at every time step. And actually, we give a negative reward, so this log fidelity is a negative number. So what this means is that our agent actually tries to kind of not accumulate a large punishment. It doesn't want to accumulate a large negative reward, and therefore it tries to find protocols that are as short as possible.
Okay, yes. Because like sometimes you can give a sparser reward, and because with this reward, basically you're getting signal every time you get closer. Mm-hmm. But you may be in an area where you can go around states and get a small penalty, then a larger one, then a smaller, then a larger, then a smaller, rather than reaching the smallest one. Did you find some hard patterns in the environment such as this one, or was it easier?
In this setup, no. What we actually found is that we So if our agent wasn't able to prepare the target state within, let's say, 50 steps, so we set like an upper threshold for the number of steps. And if our agent wasn't able to prepare the target state within the 50 steps, then these Q values are a bit ill-defined. And then we had problems that we got like some kind of periodic sequences that got stuck and never reached the target state. But otherwise, as long as you reach your target state up to, before you terminate an episode, it actually your Q values are well defined, and it actually works in these cases. Yeah.
Nice. And maybe a last question, if I may. So you see that you get like a good Q value from all of the states. Does this imply? I mean, you train on the subset, and then you get a good end policy for all of the states. Does this imply that your agent visits all of the states and learns about all of the states, or is it because of generalization from the network?
Yeah. So. In this case, outside of the training region is definitely generalization, and we looked at the Q values, and they are not necessarily equal to the optimal Q values. But because in the end you're only interested in the actions, it still works. But also this type of noise. So with this noise, we encounter states that our agent definitely hasn't seen during training, and it still works. So it definitely generalizes. Yeah.
Thank you for your talk. So I have a little bit general question. So if I understand correctly, so is this like preparing the target states unique? So there might be some other way, like you like for example, quantum annealing process. You can prepare your initial state and let the time evolve and go to the global ground state of another model. But of course it's less controllable, but what are the advantage of using your method?
So the advantage of using reinforcement learning in this setting?
Yeah.
So the nice thing about reinforcement learning is that you learn this Q-value function, which has much more information in it than just a simple protocol you optimize for. So this is, for example, like what I was showing here, that we only train once, and because we have this Q-value in the end, which only depends on the state, in principle, you can then get like the optimal protocol from any state. And with conventional optimal control algorithms, you can't do that. You usually optimize starting from one initial state and ending up in another state. But maybe also slightly related to this annealing. So here we use like the reward, but in principle, the fidelity as a reward, but you can also use the expectation value of your energy, and it actually also works. So you can also try to minimize the energy with respect to some Hamiltonian, and in this way get to the ground state. And you can combine this with this framework as well.
Thank you.
Maybe just a comment. Like one big difference here is that so a big difference here is that if you're doing annealing, then you don't have unitary evolution, whereas this is purely unitary evolution. That's fundamentally different, actually.
All right. Any more questions for Friederike? Okay, that doesn't seem to be the case. Then let's thank her again for her talk.